Okay, so today we have Jiri Kraus presenting multi-GPU programming for Earth scientists. Jiri Kraus is based in the North Rhine-Westphalia region of Germany and is a principal development technology engineer with NVIDIA. Jiri works as a professional performance expert for GPU high-performance computing applications and has over 14 years of experience in scientific computing HPC. The primary focus of his current work is multi-GPU programming models and has recently contributed to the development of extensive training workshops on multi-GPU computing offered at the SC and ISC conferences, as well as some recent publications in hydrogeologic flow modeling using GPUs. We're grateful to have Jiri with us today and present his expertise as part of NCAR's GPU computing workshop. So go ahead and Jiri, the floor is yours.
Yeah, thanks for the introduction and yeah, giving me the opportunity to present this. I happy to take any questions that come in intermediately. So I try to watch the chat a bit, but but I will also leave questions, time for questions at the end. So a bit of marketing I got usually asked for is embed what I'm talking about into the NVIDIA software stack. And that's part of the MAGNUM IO stack, which is a kind of abbreviation for multi-GPU, multi-node input-output. And that is the technology umbrella for everything networking related, where it comes to moving data in and out of multiple GPUs in a larger system. So, and today we will touch a bit on in-network compute and network IO, where communication between GPUs is covered. We're not covering any management and we're not covering storage. So what are the technologies and libraries in MAGNUM IO? There's the HPC-X toolkit, which contains a CUDA-aware MPI, an OpenSHMEM implementation, UCX, HCOLL, which is UCX is a low-level CPU-centric GPU-aware communication library. HCOLL, which is a library to accelerate collectives to leverage all kinds of technologies like NCCL, SHARP, or DIRECT, and is intended to be evolved into the UCF project UCC, which stands for Unified Communication Collective, so it uses the same umbrella as UCX, and NCCL SHARP plugins, so that NCCL can also utilize SHARP for collectives. Then there's a NCCL Collectives Communications Library for GPU-affiliated communications, NVSHMEM, an OpenSHMEM implementation for NVIDIA GPU supporting GPU-initiated communications, and there are the GPUDIRECT technologies, peer-to-peer, RDMA, and JACOBI. There's also accelerated switch and packet processing for virtual switching, and the data plane development toolkit, where it is for about packet processing in user space. Today, I will cover in different intensities on the technologies highlighted in green. I will mostly focus on MPI and how to use that from your application, because I anticipate that this is probably the most relevant for your work, how to use it with tools and how to express communication computation overlaps, some optimization tricks. But I will also talk a bit about underlying technologies like UCX, how to leverage HCOLL from MPI. And I want to start my presentation with a quick outlook on how to use NCCL and NVSHMEM, because that can be, for some cases, very interesting technologies that you can explore to improve the application of your, the performance of your application. And both are fully interoperable with MPI. So you could, if you have an MPI application, you could just apply them at places where it makes sense. Okay, so let's take a look first at NCCL. I'm sure there's most of you have already heard about it. It's a library for optimized inter-GPU communication, and the abbreviation actually stands for NVIDIA Collective Communication Library, because the focus of NCCL is really collectives, like all reduce and so on. It virtually, so I would say when it comes to GPU accelerated system, it supports all the connection that's relevant. It can move, if available, it can leverage NVLink efficiently. If available, it leverages PCI Express efficiently if needed. It can communicate over shared memory. It can leverage RDMA networks like InfiniBand and also other networks. And if needed, it can even work on sockets on any network. So a brief look at the Nickel API, which is probably, if you know MPI, should be quite familiar with you. So you create a communicator, which requires some out-of-band communication. So the process is usually root rank creates a unique ID, which is broadcasted to all other ranks, and then all the Nickel ranks call Nickel com_init rank, with that unique ID. And then this communicator can be used to carry out communication. This communication is CPU initiated, but fully executed by the GPU. So it is the communication is submitted into CUDA streams and therefore asynchronous with regard to the CPU launching that operation, but bulk synchronous with respect to the stream. So every compute work launched in the same stream will finish before a Nickel operation has started, and no other GPU work will start submitted to the same stream that before the Nickel operation has completed. So there are collective communication routines, just a selection here, which you can see, which are modeled closely after MPI collectives, so should be familiar to most of you, hopefully. And a relatively recent addition, it also added point-to-point communication APIs, which are very similar to MPI point-to-point, which can be used to express all the communication patterns not directly expressed by a collective by just using send-receive. So why is that potentially interesting for you? Because in some cases you can, as you will later see in examples, you can organize your compute and communication more efficiently if the communication can follow stream semantics, so that you can prepare a communication step that should follow after a kernel while the kernel runs. And that is something that Nickel allows you to express, because you can launch the kernel while that runs. You submit to the same stream the Nickel operation for the communication that should start immediately after that has finished. The other technology I want to touch on before diving into MPI is NVSHMEM. And for motivation, so if you're consider, for example, MPI and CPU initiated communication, we have the mode of the CPU launches the CUDA kernel, then control transitions to the GPU, the CUDA kernel is executed, the CPU synchronizes the CUDA kernel, and then the CPU carries out communication on the data modified by the GPU kernel. So we have 2 times a context switch from the control flow going from the CPU to the GPU and then back, and then probably in the next iteration again. So we are we always need to synchronize under communication and compute boundaries, which is very commonly used, and is also the model that you're doing with MPI when you combine it with different programming models, as you will see later. But the problem is that it puts these synchronization and launching kernel stuff on the critical path of the application, and you don't get overlap between the communication and the compute, so not the maximum efficiency. You can get overlap, as I will show later by the example of MPI, but that definitely adds complexity and also some overheads. With NVSHMEM, you get enabled to do GPU-initiated communication, so that you can do the compute on the GPU, and as soon as data is computed, you can initiate communication on it. So you would launch a kernel that computes and issues, for example, put operations. And that minimizes the offload latencies, because you have to launch fewer kernels, have to synchronize less often, and there's no context switch between the CPU and the GPU. It also, in case, because these communication can be relatively fine-grained, it gives you computation overlap by threading. So you get the same benefit of latency hiding for inter-GPU communication as you get of latency hiding with just regular memory accesses from the GPU. Because as you've been introduced before, if you use a GPU, you're vastly oversubscribed. You're each shared multiprocessor in the GPU with many threads, so that if one thread waits for data, another thread computes. And with NVSHMEM and GPU-initiated communication, the same works there. And sometimes it's easier to express algorithms with inline communication. Since that is a bit far away from MPI, where I assume most of you are familiar with, I want to show some brief code examples, how it looks like. So the most fine-grained way to communicate with NVSHMEM is thread-level communication. So as soon as a thread has computed a value and it knows a neighbor needs it because it's computing something on the boundary, the thread just puts that single value to the neighbor that needs it. So we get a very fine-grained communication, and if it's running over, and if that communication happens over NVLink, it's also running very efficiently because like memory, this will effectively be mapped to load stores, and like those are like load store, the load stores will be automatically coalesced like memory accesses in the GPU. On networks like InfiniBand, this is a bit too fine-grained because for every individual request, we would need to generate a network packet, which has too large overhead for very small packages. So it's also possible to cooperatively send larger blocks of data. And that works more efficient over, as I said, over networks like IB. In this case, again, compute is the same, and you don't need to leave the kernel. But now you just see, hey, am I a block that has data to communicate? And then all the threads in the block call into such a cooperative thread group communication API to send, hey, immediately after it's computed, the data of the whole block to the receiving PE. So that's, I said, that is a benefit that allows, that gives you a transparent GPU communication computation overlap due to threading. It also minimizes the number of GPU kernels you have to launch and synchronization points. So just moves CUDA API out of the critical path. So already very good, but with GPU-initiated communication, you can even get one step further, and that is move also the iteration, the synchronization into the kernel, and therefore, for example, an iteration. This sometimes can be very powerful because it allows you to merge kernels which are interleaved with communication, which would not be otherwise possible. And by merging these kernels, you might be able to keep application state much closer to the processor because you don't need to write registers out to the GPU's global memory, or you don't need to write shared memory out to the GPU's global memory from one iteration just to reread it in the next. So that can sometimes, if it's applicable, be really significant performance improvement. Not so much because of more efficient communication, but because of the fact that inline communication allows to hold state closer to the processor for a longer time. Communication used here is the same. It's just that pointing out that you can put the full kernel there, and that NVSHMEM provides API to synchronize between processes. Just pointing out here, the right synchronization strategy largely depends on your algorithm and also the system you're looking at. Okay, so before jumping to MPI, a motivating example for NVSHMEM, I've chosen CUDA, which is a library for algorithms less relevant in lattice QCD simulations. And with this field, strong scaling is very important. And here, this is a benchmark executed on the Selene supercomputer that we have at NVIDIA, and we scaled from 8 to 512 GPUs with a local lattice size of 16 to the power of 4 in case of 512 GPUs and compared MPI to NVSHMEM in different precisions. And so the smaller the data type used, the more latency critical the application becomes and the more communication bound. So we see here that NVSHMEM greatly helps to reduce that overhead and achieve better computation overlap, because we see an up to 1.6x speed up at 512 GPUs with half precision when comparing MPI and NVSHMEM. And yeah, as a reminder, there's no need to rewrite your whole MPI application to NVSHMEM or NCCL. It's fully interoperable, and you can just apply it for the places where it makes most sense. Yeah, I'll keep that here as a summary of NVSHMEM for further reference. And also want to point out that yeah, the NCCL and NVSHMEM they are fully, as said already, fully interoperable with MPI. There exist Fortran bindings for both, which are provided with the HPC SDK. And if using the host APIs, and it's also interoperable with OpenACC, because you can, using the OpenACC interoperability API, to get a CUDA stream for an OpenACC SNQ or set a otherwise created CUDA stream to an OpenACC SNQ, and therefore you could also use NCCL in parts of OpenACC applications the same way, almost the same way as you can use the CUDA-aware MPI in an OpenACC application. Okay. Now to the main part of my talk today, CUDA-aware MPI. So I assume you're all here because you want or need to program a cluster with multiple nodes and possibly multiple GPUs per node, and need to use that to solve larger problems or a given problem faster, and so that all these GPUs work together on the same problem. And that for that, at some point, this GPU need to exchange data so that you are really coordinating on solving the problem and just not solving many similar problems totally independent of each other. And yeah, usually what I say here is, if you know GPU programming with CUDA, OpenACC, standard language parallelism, and you know MPI, then I don't have to tell you much more. Just use a CUDA-aware MPI, and things work as expected. So if you use a CUDA-aware MPI and pass a device pointer to the MPI knows how to handle that, move data in the most efficient way from the source buffer to the destination buffer, and things work as expected. Yeah, of course, I'm not ending the talk here because there are some things, tips and tricks to share, and probably some internals to understand to better reason about the performance behavior of the applications. To get everyone on the same page and set the stage to avoid losing some who might not be that familiar with MPI or new to that, this is not an MPI tutorial, but I want to try to capture your anyway. Let me give a very simple introductory example that hopefully allows you to follow the rest of the talk if you're not that familiar. For that, I'm using a JACOBI solver, which, in case you're interested in the math, but not necessary, solves a 2D Laplace equation on a rectangle. And I'm using directly boundary conditions, so constant values on the boundaries. For the examples here, I'm using a 2D domain decomposition. So I'm cutting the domain in rectangles with n by k domains. So how does the implementation look? We have a while not converged loop, and in every iteration of the loop, every rank applies a so-called stencil to an array U and stores the result to U new. So that means for the interior part of the domain, so leaving out a boundary, which is necessary because the operation effectively calculates the average of 4 neighboring points and stores it here. So we cannot do this for the boundary values. we iterate over all interior points of our domain. And then, because the domain is distributed across all GPUs, cut into these pieces, we need to make sure that the updates we have computed are visible to the other processes in the participating in our job execution. And for that, we use so-called halos, which means the last interior row of each process and last interior row, last interior column, first interior column, first interior row is replicated to the right, bottom, top, or left neighbor. And then after each iteration, we need to send this row to this replication, which is the boundary of the other one, so that it has up-to-date data in the next iteration and really threads are cooperating. Then we swap the roles of you new and you and start the next iteration. And with how does that look like with OpenACC and CUDA? I'm using here for brevity on the slide MPI send receive. In most applications, you would probably use non-blocking MPI like I receive, I send, wait all patterns, but this is just to keep the slide a bit more brief. So in case of OpenACC, because we compute on the GPU, we need to use the Pragma ACC host data use device because to pass the right data to the MPI library. That is necessary because from the OpenACC compiler's perspective, the MPI call is a CPU call. And usually an OpenACC compiler derives from context if it should use the host representation, so CPU representation of a symbol like you knew, or the device representation of the symbol. Since we have modified with a previous kernel the data on the GPU, we want to use, of course, the device representation. And that is what we tell the compiler by using Pragma ACC host data use device, that in the following structured block, the device representation should be used, even if we are calling into CPU functions. And then we have two send receives for top and bottom halo exchange. The first one sends to our top neighbor, and at the same time sends to our top neighbor, and at the same time receives from our bottom neighbor. The first row modified and to the bottom boundary. The second call sends to our bottom neighbor, and at the same time receives from our top neighbor the last row representing the top boundary. In CUDA, this looks exactly the same, except that there we have a direct pointer to the data we have modified on the GPU. In contrast to that, if you would not use a CUDA MPI, so the MPI is not able to handle device data directly, we would first need to copy the data from the GPU to the CPU, then which would be done in OpenACC with a Pragma ACC update host, do our communication, and after the communication is finished, because then the communicated data is at CPU memory, copy the data back from the CPU to the GPU before the computation can continue there. Conceptually with CUDA, we need to do the same, but it just looks, we don't use a Pragma, but an API call. CUDA MPI also works with standard language parallelism, for example, Fortran do concurrent or C++ did par. And these implementations available with the HPC SDK rely on unified memory. So there is no need for any data clauses or copying, because every pointer you use is unified memory and therefore usable on every processor in the system. And it just migrates where it's most used. And to showcase that, I've used the left-right hero exchange, where we usually, because sending individual elements is very inefficient, so we usually need to tag to a larger communication buffer, which we, in case of ISO C++, could do with this for each parallel loop for packing. Then we do our communication, and then we need to do unpacking after communication is finished. Yeah, as said, because we're using unified memory, there's no data clauses, no copying required. The CUDA-aware, all current version of CUDA-aware MPI implementations are aware of unified memory and know how to handle it. With OpenACC, conceptually, we need to do the same, just that, of course, again, we need to use the host data use device directive to pass the right data into, and we want to do the gathering and scattering of our non-contiguous data in GPU memory. So they do that with OpenACC generated GPU kernels. Same, of course, with CUDA, just there we use kernels instead of relying on the compiler to generate them. Okay, so there are two more things which I want to mention, which are a bit different to just using MPI. One is launching MPI plus CUDA OpenACC programs, and I'm pointing that out because some CUDA-aware MPI implementations require you to enable CUDA-aware features at runtime. Of course, if you build them from source, they need to be configured with CUDA features, but if there's are, you still need to enable. So OpenMPI has the CUDA-aware features enabled by default. MVA pitch needs to set this environment variable, Cray also an environment variable. IBM Spectrum MPI has a switch to the launcher, and Parastation MPI also MPI variable. The other aspect is handling multi-GPU nodes. So, for example, consider we have 4 nodes with 4 GPU each and launch 1 MPI rank per GPU. We would end up with 16 processes, 0 to 15. And let's assume our job scheduler distributes them consecutively on each node. So first node has 0 to 3, second node 4 to 7, and so on. Now, if you don't do anything with handling GPU affinity, so no CUDA set device, no ACC directive to select a device, they would all just pick device 0. So on every node, you would oversubscribe GPU 0 and leave GPU 1, 2, and 3 idle. The question now is how to select a device, especially on the second node, because there's no device 4, and how to come up with the right device ID to choose. So what I usually propose is determine a local rank, which can be done by using MPI COM-split type, using the type COM-type shared. COM-type shared gives you a communicator where all MPI ranks in that communicator can communicate via shared memory. And that effectively means that it's all MPI ranks running on the same node. So we create such a new local communicator, query that local communicator for a rank, and then we no longer need that, so we can immediately free it. So visually, that means we have still our MPI COM world with ranks 0 to 15, but we now have split it up into 4 per node communicator with ranks 0 to 3. And we can use these local ranks to call CUDA set device to select the right rank or the equivalent OpenACC directive. So what I have also added here is querying the number of visible devices and do a modular operation. Yeah, that's done for 2 reasons. First of all, as I introduce later, in some cases, it might be worthwhile to launch multiple MPI rings per GPU. So that would be supported then by that. So because you might have more MPI rings per node than you have GPUs. And secondly, there are some MPI launchers, or you might use a launcher script to handle the GPU affinity externally to the program, so that nothing like CUDA set device is needed in your code. Related to that, external resource managing, external GPU affinity handling. Conceptually, it does something like I've shown in this script on the left side. So I've shown here the node topology of the node of the Joules booster, the system at JFC in western part of Germany, where I'm from, with 936 nodes and 4 A100 each, and the and how to map this topology to a good job execution with using a launcher script that just sets environment variables so that your application don't need to handle GPU affinity. To determine the right values, what I want to point out here is the tool NVIDIA SMI Topo-M. NVIDIA SMI is the tool to manage the GPUs in a system, and the Topo sub-option provides you a topology view and gives you this connection matrix saying you how GPUs are connected with each other, if they're connected with NVLink, and how they are connected to the network adapters in the system and which are the local CPU affinity. So based on the information provided here, using environment variables set by the launcher on the system, in this case it's Slurm, and I use Slurm local ID, which corresponds to the local rank returned by the MPI calls I have shown before. If I'm rank 0, I want to use GPU 0 because GPU 0 has a fast single PCI Express switch connection to the Mellanox adapter 1. I set UCX net devices to Mellanox adapter 1, and the closed CPU cores are 18 to 33, so I set CPU bind. I do the same for rank 1 and GPU 1, rank 2 and GPU 2, and so on. And then I just use NUMA-CTL to bind to the correct CPUs. The environment variable takes care of the network adapter and the GPU, and then launch my application. So that could be part of a script where your job execution is just prefixed. I first of all wanted to point you out as a trick to optimize performance of your application, but also because actually on some systems, the job scheduler automatically does this. This is, for example, the case for the Joules booster system. There, if you launch a job with SRun, it will automatically set CUDA visible devices and bind your processes so that you're effectively using the system. Okay, that is, I would say, really just to get started, all you need to know to run, use MPI to program multiple GPUs in a multi-GPU system. The remainder of the talk will explain you some fundamentals, how things work internally and why things work, and how to use tools to allow you to analyze and optimize the performance of MPI+CUDA, OpenACC, standard language parallelism codes, and reason about the performance behavior. First, why does it all work? How does the CUDA-aware MPI know that a pointer is a GPU pointer and it needs to be handled differently to a CPU pointer? The enabling feature for that is unified virtual addressing, not to confuse with unified memory, which is also sometimes abbreviated as UVM, unified virtual memory. It's really not unified memory or managed memory, it's unified virtual addressing. So the memory that's, for example, allocated with CUDA analog is pinned memory on the GPU. It cannot move, so the virtual to physical address mapping stays the same, but it's still part of a unified virtual address space. So what does it mean? If I have unified virtual addressing, all the memory allocations of a processes are put into a contiguous address space. And a certain part of the address space is reserved for CPU allocations, a certain part is reserved for every GPU. And that allows that you can determine the physical location of a pointer by its pointer value and allow a library, like, for example, a CUDA-aware MPI, to query a pointer where it points to and then take the right decision to move the data. Other relevant technologies are GPUDIRECT, because they allow to move data faster between GPUs. I want to touch on the two important ones, peer-to-peer, which allows to move data directly from the memory of one GPU to the memory of another GPU in the same node over NVLink, without any intermediate staging in CPU memory or even CPU involvement. And then there is GPUDIRECT RDMA, which allows a non-GPU device to directly read and write GPU memory over PCI Express. This can be leveraged by network adapters to directly read or write GPU memory and send it over the network without intermediate staging in CPU memory or CPU involvement in the transfer. To highlight the performance effect of this, I've chosen a very simple example where MPI rank 0 does an MPI send from a GPU buffer, and MPI rank 1 does an MPI receive to a GPU buffer, and the matching communication. This is to show how CUDA plus MPI works in principle. Depending on your MPI implementation, your system setup, your message size, the situation might be different. But still, I think it will help you to understand the performance behavior of MPI communication between GPUs better. And we are looking at 2 GPUs in 2 nodes. So first, we look at the case that we have a CUDA over MPI with support for GPUDIRECT ADM. In this case, we call MPI send on the source buffer in GPU memory and MPI receive on the destination buffer also in GPU memory. And MPI takes care to directly move data over the network from source to destination buffer without touching any intermediate buffer on the CPU. If we analyze that with Nsight Systems and create an application trace and look into that, I've done this for the OZU bandwidth benchmark and also sampled GPU metrics to see activity on the PCI Express bus. What we see is first that we don't see any GPU activity because all the transfer is carried out by the network adapter. So these are the direct reads from the network adapter. So we don't have any CUDA API calls. We don't have any GPU activity, but we see PCI Express activity because these are the reads of the network adapter from GPU memory to move the data. In contrast to that, if we have a CUDA over MPI without support for GPUDIRECT, we call MPI the same way because the MPI knows how to handle GPU data. However, because it can't move data directly, it needs to stage between intermediate buffer and CPU memory to move the data. This can also be seen in the same profile. Now we have a pipeline executed. We have multiple chunks of device to host transfers because before sending data on rank 0, data is copied from device to host and then transferred over the network in chunks. Last, in steep contrast, also if we have a MPI without CUDA support, so need to copy manually in the application side from the GPU to the CPU before starting our communication and copying from the CPU to the GPU after we have received data. Of course, there are more intermediate copies involved, but also the pipeline stalls after moving data to the CPU and after moving data with MPI. So we have more steps and pipeline stalls. And that can be also seen in the Nsight system trace. So we now have not a relatively efficient pipeline of device to host mem copies and network transfers. We have one large device to host transfer and then the network transfers. This is just the source rank. This can be also seen when looking at performance. So when I look at the performance of internode transfers with a regular MPI, we see we are limited by 10 gigabytes. With the CUDA MPI, without using GPUDIRECT RDMA, we get almost twice the performance because we can execute in the pipeline, but we are still limited by executing in performance by executing the staging pipeline. And we can really saturate the available network bandwidth if we can use GPUDIRECT RDMA. This has also a significant effect on latency. For intranode transfers, which can map to NVLink, the bandwidth delta is even more severe because the NVLink connections between GPUs have far higher bandwidth. Okay. Closing this internals one with a short collection of UCX tips and tricks. And why am I mentioning this? Because so you might wonder, what is UCX? That's a communication framework not intended to be used by application developers directly like you, but to be used by communication libraries like MPI. So many MPI implementations build on UCX to implement the actual data movements. Therefore, actually, the data movement I've shown you is, while you call MPI, it's not executed by MPI. The buffers are just passed through to UCX, and then UCX moves the data. So that's important to know, because when you want to tune performance, you don't need to look for MPI parameters. You need to actually look for UCX parameters. And to fine tune things like protocols, thresholds, to switch between protocols, and so on, UCX interprets a lot of environment variables. So the first tip I want to show you is that these point you to the fact that UCX is used, and in many cases, and that UCX exposes environment variables to influence its behavior. And the second one is that you can use the UCX_info program that comes with every UCX installation to query which MPI, which environment variables are interpreted and what are their default values. For example, the rendezvous scheme, when you look at the output, has 3 different modes: auto, a get-based protocol, a put-based protocol, and here it's also some explanation. You can also find some information about this environment parameters on the UCX wiki on GitHub. And 3 I want to point out. One is, you have already seen, UCX net devices, which is a list of network devices that the processes with that environment variable set are allowed to use, which is sometimes helpful to tune performance. There's always work to improve the heuristic to select the right device. So depending on the UCX version you're using that and the system you're on, that might help performance or might be effectively no op, because the UCX internal heuristic already does the optimal thing. Then for debugging, there's UCX memtype cache. So querying where a pointer points to comes with some overhead. And to amortize that overhead, UCX maintains a cache where a pointer it has already seen points to. If it's a CPU memory, it's GPU memory. And to keep that cache up to date, it needs to know when buffers are deallocated. And for that, it does some tricks to intercept CUDA free calls and so on. But in some cases, these tricks don't work out, and then the cache can become stale. And that can, for example, result in segmentation faults or errors like that, and or in worst case, corrupted data. And to rule out issues with the cache, it's sometimes helpful to disable the UCX, the memtype cache, by setting UCX memtype cache to no. Another thing to debug and do a performance experiments is UCX TLS, which is the list of transports UCX is allowed to use. The ones I want to point out are the ones related to moving data in and out of the GPU. And these are CUDA copy, CUDA IPC, GDR copy, which are summarized under the CUDA TLS. So CUDA copy is the staging pipeline I've shown. CUDA IPC is using CUDA IPC, CUDA inter-process communication, to utilize NVLink to move data. And GDR copy is a technology for used to leverage GPUDIRECT RDMA for low latency communication. In addition to that, the typical for internode, for example, on InfiniBand, you usually use the TLS RC or DC. And then you can play around sometimes to debug performance issues or understand performance better, or correctness issues by disabling certain transports. For example, you could exclude CUDA IPC GDR copy from your list of UCX TLS, and also set UCX IB GPUDIRECT RDMA to no, to disable all variants of GPUDIRECT RDMA, and see how it impacts your performance, or maybe solve a problem because something is misconfigured on the system you're using. This is the combination I've used to run the experiments with GPUDIRECT RDMA enabled or disabled I've shown before. Okay, let me switch gears and go to collectives. Brief introduction of the hierarchical communications algorithms library, HCOLL, which is a library I already mentioned in the beginning for software and hardware accelerated collectives. So it can leverage, for example, a nickel backend for highly tuned late data collectors in GPU memory, but it also comes with its own highly tuned communication libraries for CPU and GPU data. And it can also leverage hardware acceleration, for example, the scalable hierarchical aggregation and reduction protocol SHARP for in-network switch computing, and CORE-DIRECT. The first, it actually, I'm using that for my experiments, but this project actually just evolved into a successor project, Unified Communications, which is under the UCX umbrella, and the first release was done with HPCX 2.11 released this April. MPI implementations can link to UCC or HCOLL to accelerate, to improve the performance of their collectives. And for example, OpenMPI has that feature. And I've run 2 performance experiments on Selene with 16 to 512 GPUs, so up to 64 nodes. And I've looked at the latency of an 8-byte all reduce of 2 float values, so an 8-byte all reduce float out of place. And I've compared the plain OpenMPI performance just using HCOLL and using HCOLL and SHARP. And what you see here, that with HCOLL, you get far better latency, and you get better latency than with OpenMPI. So that's an optimized algorithm. And this is even further improved with SHARP, which gives you almost flat latency irrespective of the scale. For large collectives, now switching to 1 gigabyte, so for example, relevant in data parallel deep learning training, the differences get even more severe. So if we utilize HCOLL with the nickel backend and SHARP, we can fully saturate the network bandwidth and get so the per node bandwidth is actually 192 gigabytes. And so we get even an amplification factor by the network compute and get an almost flat performance over the number of GPUs. Here, the OpenMPI performance is totally not competitive. I'm just plotting it here for completeness, not for comparison, because for GPU data, the plain implementation OpenMPI is just known to not be very highly tuned. So if you have large reductions to do, it's really advised to use something like HCOLL or UCC. If you want to accelerate nickel as the backend, there is some limitations you need to be aware of. First of all, nickel accelerated collectives do not work with MPS, and you have to consider which thread mode to use. And if you're using blocking and non-blocking collectives, then there are some restrictions apply which communicator you can use. This is enabled by setting HCOLL CUDA bcall to equals nickel, and then if the nickel chat library can be found by HCOLL, it will be picked up. Important point out, the restrictions here are not checked by HCOLL, and they don't enforce it. So if you violate them, you might run into deadlocks or corrupted data if you're using unsupported combination. So that's just as caveat here. Okay, switching gears again, going to GPU acceleration of legacy MPI apps. So when you have an MPI application written without GPUs in mind, so large parts of the code is only MPI parallel, but you want to GPU accelerate, so you have already accelerated the hotspots kernels, and now want to have an early return on your investments. You want to see a speed up kernel. So what often happens if you, for example, have an application very simplified structured like this, where you have a serial part that's not parallelized at all. The rest is parallelized with MPI, and part of it you have also parallelized with GPU. So this is not amount of code, but runtime. If you scale that code on the CPU, it scales nicely with MPI as the original code. And if you go to the GPU, you also see a nice speed up of the GPU accelerated part, but you don't get an overall speed up because you don't scale up. You're not benefiting from the scaling of multiple MPI rings of the not yet GPU accelerated parts. And that is where multi-process service or MPS comes in, because you can just launch multiple MPI rings per GPU so that they share the GPU, and you can combine the GPU speed up of the already accelerated part with the MPI scaling of the not yet accelerated parts. So sometimes I get the question like, that's actually what I would expect it to be possible anyway. So why do I need MPS? Why don't I just launch multiple processes per GPU? Reason is that how the GPU works. And if you don't use MPS, each process has a separate context on the GPU. Context is kind of an equivalent to a process on the GPU. And now in the GPU only serves one context at the time. So different contexts can be active on a GPU at the same time, but they're time sliced using it. So first process A executes, then process B, and so on. So we are not really both are not really using the GPU concurrently, even if they are free resources. And also, not only that the operations are serialized, there's also a relatively costly context switch overhead between when work is switched between one context and the other. Both can be avoided by using MPS. Then both processes can submit work to the GPU concurrently, and this work can execute concurrently if there are free resources. And we also avoid the context switch overhead. A real-world example is RELION, which is a post-processing tool for crystallography imaging, and it benefits from MPS. And there, the oversubscription enables multiple things. So it enables, for example, overlapping the copy with the compute of a different process. It enables overlapping of compute of different processes. So these small kernels from one process overlap with a longer running kernel from another process, not using the whole GPU, and therefore provide a more efficient compute execution. Using MPS is easy. No application modifications are necessary. It's not limited to MPI applications. So you could also use it, for example, to pipeline, to use multiple instances of your post-processing tool, where then the file I/O of one instance is overlapped with the GPU compute of the other using the same GPU. Everything happens with the MPS control daemon, which just needs to be spawned, started before the application startup, and then takes care of spawning MPS servers. And what I also want to mention that with the Volta architecture or compute capability 7, there have been some improvements with MPS, both in terms of overhead and isolation, but also with provisioning and quality of service. So you can set, oh yeah, that's a good point. Sometimes you're done by Daniel. I would say on most systems reasonably administered, you don't need to, you need to take care that MPS is started, but you don't need to do it with a manual process I'm pointing out here, but rather with a command to the to how to allocate your job. Okay, so switching gears again, looking into tools for CUDA applications and how to use them in an MPI environment. I've seen from the agenda, you have already got an introduction to tools. in this series of talks. I'm not going to reintroduce the tools. I might repeat some parts because they fall into that one, but mostly focus on how to use the tools listed here in combination with MPI programs. So I'm covering memory checking with COMPUTE-SANITIZER, debugging with CUDA-GDB, and profiling with MSite systems. Generally, the approach for multi-process tools is that they're all for work on a single process. And what we are leveraging here, that many bugs and performance issues in parallel programs are actually serial bugs. So it's not necessary to look at the whole picture. It's just necessary to look at to debug a single rank of it. And so the basic idea is we just run the tools n times in parallel, one for each MPI rank. And how does it work? It works because the tools allow to specify output files with a special, all the tools support to put a special syntax into the output file name specification, %q and then curly brackets. And then when generating the output file, evaluate that the environment variable named in the curly brackets. And here, then the environment variable should be replaced by something used by the process launcher so that a unique ID per output is done. No worry, I will show some examples of this. And just one thing you could, for example, use if you use an OpenMPI-based launcher, you could use OMPI COM-WORD-RANK to put into this one, or if you use a Slurm-based launcher, Slurm PROC-ID. Okay, let's look concretely what this means for COMPUTE-SANITIZER. Just recap, COMPUTE-SANITIZER is a collection of tools where memcheck, which is the default tool, is comparable to Valgrind's memcheck. But there are also other tools to check for shared memory data access hazards, for uninitialized device memory, or for wrong synchronization. I don't go into the details of these tools, just how to use COMPUTE-SANITIZER with multiple MPI ranks. And that works, as already explained in an abstract way, by launching one instance per MPI rank. So after our, for example, srun, we put COMPUTE-SANITIZER. And then we make sure that every instance of COMPUTE-SANITIZER writes to a different output file by using this %q curly brackets syntax. And then finally, of course, our application. And that, in this case, stores two output files, one textual output in the log file and one raw binary data output per process. And then we can inspect this, either take a look at the log file or inspect the binary output by reading it with COMPUTE-SANITIZER. One tip here, most probably to repeat, if you use COMPUTE-SANITIZER, compile your code with -line info to get line correlation for device code without getting the full overhead of debug information enabled with -G. Yeah, then if you look at the individual output files, the output looks less familiar as you know them with COMPUTE-SANITIZER. For example, an out-of-bounds access in this line would look like that. We have an invalid global read, and then the thread is pointed out, and which, if compiled with -line info, the source code, the source file, and the line info, the line where this actually happened. Okay, that's often, I would say, this tool can solve already a lot of bugs, and you don't need to dive deeper, but sometimes you need to dive deeper with CUDA-GDB. And CUDA-GDB also works with MPI, for example, with the usual tricks that you can use with GDB. Of course, you need to compile with debug symbols, not only on the host with -g, but also device debug symbols with -G. Be aware, this really slows down your application. So you only want to do this for debugging runs and probably want to size down your problem where the problem reproduces. And yeah, the first trick to work with GDB with MPI is just a general GDB trick. You just attach later. So you add code like this, that the rank you want to debug prints it's the host name it runs on and the PID, and that it's ready to attach, and then enters an infinite loop so that you can log into the node where this MPI rank then is stuck, attach with CUDA-GDB, and change the variable so that the rank exits that loop, and then you can start debugging your problem and hopefully identify the issue. Next, there are some things that makes it more convenient. For example, what I just shown, in case of exceptions, this process is actually automated by the CUDA driver. By setting CUDA device waits on exception, the CUDA driver does exactly what the code I've just shown does in case a device exception occurs. It prints the host name, where it happens, and the PID, and holds the processes so that you can use that information to log into that node and use CUDA-GDB to attach to that process and inspect the program state to hopefully root cause the error and then fix it. Sometimes this is this interactive debugging just doesn't work because the scale where the problems occur is too large. And in this case, you can also generate cordons. And the environment variable to set for that is CUDA enable cordon on exception. And then there are two other relevant environment variables to name out. First of all, you can include a CPU cordon or not. And you can avoid dumping all application memory to make it faster by setting CUDA enable lightweight cordon equals 1. Then after your error reproduced and you have the core dumps, you can just start CUDA-GDB and open your core dump as you're used to opening core dumps with GDB, and inspect the state of the CUDA core dump and to hopefully root cause your error and fix it. And of course, there are specialized parallel debuggers with far more convenient interfaces and more powerful features. So yeah, in this case, so if you have access to those, yeah, really use those. For example, ARMDDT or Perforce Total View are very powerful parallel debuggers, also with support for CUDA. Okay, now you should hopefully understand how CUDA-aware MPI works in principle, why it works, how to correctly launch it, how to fix application bugs. So next thing is to look at performance. And that can be done with the Nsight Systems profiler, which looks as the whole application in contrast to Nsight Compute. So in case of MPI, so the per kernel optimizations with Nsight Compute would happen on a per rank basis. We're not covering that here. We are focusing really on the timeline behavior, which is relevant for parallel applications with Nsight Systems. Similar to the debugging tools, we use the %q syntax and generate and launch one instance of Nsight Systems per MPI rank to get one application trace per MPI rank, and then we inspect the results by opening the report file in the GUI, or use or on the command line, for example, with the stats option, which gives you an output like, for example, this initial high-level overview where most of the time is spent. In Nsight System, you're just open, and then you get a timeline like this, where you then see if you profile with MPI tracing enabled, you also get extra information like labeling of processes with MPI ranks, labeling of context with MPI ranks. You get MPI traces overlaid to those, and yeah, all the familiar features of Nsight Systems. So you can really also inspect the communication behavior. And you can also add multiple reports to one single view so that you can see, can correlate the behavior of different MPI ranks. And for example, here see that this all reduce probably takes longer because something is delayed on rank 1 because something is delayed in rank 0. And also, if you click on the individual MPI buttons, it gives you MPI sections. It gives you some information like what is the source rank, destination rank, how large is the message that was exchanged. As with debugging, there are also other tools which are more powerful for large-scale profiling, and which might be necessary because, as same as with debugging, detecting issues at scale of thousands of GPUs is really complicated. So you need to slice and dice data because there's just too much data to make sense by looking at the timeline as NCAR system presents you. The community tool, a very popular community tool, which is CUDA-aware SCORP. So you can use SCORP to instrument your OpenACC or CUDA or standard language parallelism application and generate a SCORP trace. SCORP internally use the CUPD, CUDA Profiling Tools Interface API to get information also about GPUs. Yeah, then you collect that trace, and then you can analyze it with all the performance tools that know SCORP, for example, VAMPI or Tau, and so on. Yeah, here's just one example of a VAMPI screenshot with a CUDA timeline of 4 processes. Okay, so what do you do with, I want to close the talk with some optimization tips to work around common MPI performance issues. First, I've run a scaling experiment of the simple JACOBI solver I have shown you. And I've plotted the time to compute and the time to communicate. If we use only a 1D domain decomposition, which I did here, in this case, not a 2D, then the time to communicate stays flat because we always need to communicate the same amount of data, but the time to compute, of course, decreases because if I add more GPUs, each GPU computes less and less work. And that is what we see, that the runtime decreases. If we plot then the parallel efficiency, we see that this decreases with a number of GPUs added, and that's for 2 reasons. First of all, there's some overhead of coordinating the communication at all, but mostly because the relative time to so the absolute time to communicate stays constant, but our time to compute gets smaller, so the relative time to communicate gets larger. So to highlight that fact, I've also plotted the parallel efficiency if we would just ignore the time to run, to communicate. So that is obviously almost 10% higher, so some performance gain we want to have. And looking at NCAR systems profile of an MPI rank, we also see that effect. So we have our communication, and then we have our compute, and after that finished, we exchange our halos, and we see that this is done with peer-to-peer copies here. So what we're effectively doing, we process our whole domain, and then we do MPI. However, in many cases, and as in this, we can process the domain in any order. It's our choice which grid point we calculate first. So what we could do is we could split up our domain into the part that only processes boundaries, so that we need to communicate with our neighbors via MPI, do that first. And as soon as that has finished, we can kick off our MPI communication early and do it also in parallel with processing the remainder of the domain, effectively hiding the time to do the communication. So how does it work? We just launched 3 kernels. One kernel that just computes the first row of our domain into a communication stream. One kernel that only computes the last part of our domain in a communication stream. And after these 2 are launched, we launched a kernel that does the bulk of the compute, leaving out the first and the last row. And then we only wait for the work in the communication stream, so leave that running, because that is the one we need that needs to be finished before we can start communicating, and then communicate. So this way, this communication can overlap with this kernel compute. This is with CUDA. With OpenACC, concept is the same, just that we are now using directives to generate, let the compiler generate our kernels, and we use, instead of streams, we use async queue identifiers. So Q1 for the computation of the boundaries, and then a wait for that, and Q2 for the bulk compute, so that the bulk compute can overlap with our communication. Looking at the timeline, we see that this works. Now, between two iterations, we only have our all reduce left. We have our two boundary processing kernels, and we see that the MPI compute is overlapped with our bulk compute. And we still have some parallel overheads, so we didn't really achieve the compute-only parallel efficiency, but we had a significant improvement in parallel efficiency by overlapping communication and computation. Question: can we improve that further? One thing is, maybe we've seen some time to launch these kernels, and maybe if we launch them, first launch the bulk compute, we could maybe also hide the time to launch and synchronize these extra kernels by just launching them first. I've tried that and captured an inside system profile, and unfortunately, it does not work. So, because the tiny kernels to compute the boundaries where we have the MPI dependency on simply don't get resources on the GPU because the bulk kernel occupies all these resources. So we are back at the non-overlap, effectively back at non-overlapping. So, but of course, I probably, you would, as expected, probably I would not expect this if there is presented this way, if there's no workaround for it. And it is, because we can create streams with high priority. And there's also another use case where this is critical to overlap communication and computation. And that is, for example, that it occurs in molecular dynamics simulations, where you have to do communication before you can do the compute on the data that needs to be communicated again. Without high priority streams, you would end up in this situation. You overlap the communication you need to do first with your main compute, but then you can't overlap the computation that you need to communicate again, and therefore your second communication is fully exposed. With high priority streams, you can launch this compute non-local forces kernel into a high priority stream, so that the GPU prefers work from that one to schedule over the lower priority stream work, and also get overlap of the second communication step. How does that look in code? So first, you need to query the priority range of the GPU supported, and then you create two streams. And we only need two priority labels, so for simplicity, I've just taken least priority for the compute stream and highest priority for the communication stream. You can also leverage that in OpenACC by using the ACC set CUDA stream, OpenACC API, to tie a high priority stream you have created to a queue identifier of OpenACC, and then use that queue identifier in your async process. And yeah, if we do that, we get a then computation overlap of your communication with the bulk compute. Also, the launching of our tiny kernels overlap with the bulk compute, and we get a slight increase. In this case, it's not that significant. It's only a slight increase, but depending on cases, that might be larger in performance. Okay, last but not least, one last trick. Detecting CUDA awareness, which might be helpful for your build system. Parastation and OpenMPI expose via the MPI-X header some macros and a runtime function to query CUDA awareness at runtime, so that your application can warn, error out, or choose a different application path if it is compiled or run without a CUDA aware support MPI library. Parastation MPI also allow to query that information via MPI info. With that, I'm thank you for your attention, and I'm happy to take your questions. Pointing out a few more resources. First of all, multi-GPU programming with MPI GTC tutorial, which is available on NVIDIA On Demand. This has a large overlap with today's presentation, just a little bit more. Then there's a GTC talk where I go a bit more detail in comparing MPI and NVMe and Nickel for a simple using a simple 2D JACOBI solver to really compare the models performance-wise and do a bit more detailed comparison how to express the same algorithm with all three variants. The one presented here is also available on GitHub, which tend to be a very simple code written once in MPI, MPI with overlap, Nickel, Nickel with overlap, NVMe, and so that you really can compare the different models. NVMe and Nickel use MPI interoperability, and for example, the MPI version here also has examples of handling GPU affinity or detecting CUDA wins. Yeah, I hope this was useful for you, and yeah, I have time to take some questions.
Thank you, Jiri. Any questions, feel free to submit them into the chat or raise your hand and we can answer them live over voice. I guess I can have initial questions. Yeah. So you presented multiple approaches for implementing multi-GPU communication. Do you have a preferred library that balances, say, performance and, say, time for implementation and effort needed to implement those different libraries?
Oh, no, I don't really think that there is a general recommendation to make. It's really application, I would say, depending on the developer community. So what kind of portability is needed between different systems and programming models, what kind of expertise is in the developer community, then how large are the performance gains, and where the best implementation maps optimally to. For example, there could be cases where the performance benefit of NVMe is relatively small, and then it's not helpful to introduce an additional dependencies. But there could be also cases where the performance benefit is really huge, like with CUDA, or if you can use it to fuse kernels and then achieve a 2x kernel speed up because you can keep state closer to the multiprocessor. So, but nothing really is something case by case.
That makes sense. Go ahead, Helen. You're welcome to unmute and ask your question.
Okay, great talk, thanks. I guess my questions are more on so just making code portable across machines. So like one machine you might want to use Nickel, another that's not available. Is it quite easy to just wrap all these calls up in an MPI wrapper and switch out Nickel versus just regular MPI? Or are there any pitfalls to worry about if you do that?
I would say for many patterns, that's probably possible. But I would say that if you do that, that I would question if that really makes sense, because CUDA-aware MPI implementation are very efficient at moving data. So Nickel is not per se more efficient of doing a point-to-point communication.
Okay.
The benefits of Nickel mostly, when it comes to point-to-point communication, the benefit of Nickel mostly is due to the stream-aware API. And as soon as you wrap it up under an MPI one, you lose that because you no longer pass a stream in, and then that benefit is gone.
Okay, great, thanks.
Yeah. Also, if there are more questions and you're attending ISC and in the tutorial program, I want to highlight that luckily in SC tutorial I'm doing together with a colleague and the Jülich Supercomputing Center about efficient distributed GPU programming for exascale. We already did it last year SC and this year ISC, and we will do it again at SE this year. So happy to come to that. And the material, including all hands-on examples, is published on GitHub. I think that's maybe also helpful for your learning.
Thanks, Jiri. Yeah, certainly the upcoming tutorials will be very useful for participants here, and we'll be sure to share those with others. Any other questions from the group before we close out?
Yeah, I had a question. I was curious, as you had the example with GPUDIRECT using RDMA. As you're scaling out applications, do you end up running into PCIe bottlenecks, or do you have strategies or technologies to kind of get beyond if you're fully saturating channels for inter-GPU communications?
So with most well-designed GPU accelerated systems, PCI Express is not a bottleneck, and it's certainly not the bottleneck that increases with scale. Because the well-designed systems put an HCA close to a GPU so that it only needs to traverse a single PCI Express switch, and then given that the PCI Express bandwidth, depending on the network technology used, is either slightly higher than the available network bandwidth or significantly higher. PCI Express, if GPUDIRECT RDMA can be used efficiently, usually does not tend to be the performance bottleneck. And if it is, it definitely is nothing that increases with scale. The visibility might increase, but you will see that already for example, you can certainly build up the PCI Express topology of a node that is very unfortunate for GPUDIRECT RDMA communication. And that performance effect might be visible into your end-to-end performance only at scale, but you will have the performance issue already at low scale, because that is a bottleneck that will occur for every communication. Does it make sense? Help?
Yeah, that's great. Thank you.
Go ahead, Tina.
Hi. I was really interested in the way the Joules has that automatic boost based on topology. We've got a new system coming in. Was that something NVIDIA helped set up with Joules? Or I guess, how did they develop that?
I was involved in the process by advising on what the right topology is, what are good defaults. But I was not but I'm not aware that NVIDIA was involved in actually implementing it. So, but what effectively the system does on a very high level is summarized on this slide. So effectively, the job scheduler uses the NVML API, which is the library that's also used by NVIDIA SMI, to query the topology of the system, and then it just sets these environment variables in the launcher.
Thank you. This is a great resource. Yeah,
but that's effectively what the job scheduler does. It generates a launcher script like this, and then I'm not enough into resource managers like Slurm to provide any more tips like that. Yep.
Thank you.
Well, barring no further questions, I want to thank Jiri for his time today and offering his expertise on multi-GPU computing, especially with the time change all the way to Germany. So I appreciate you staying on late in the day for us. Our next section in the GPU workshop at NCAR will be an interactive session focusing on some hands-on work, implementing some of these techniques we learned today. So look forward to that in our next session 2 weeks from now. If you have any follow-up questions, feel free to message us in the Slack. And if you would like to have a follow-up question with Jiri, feel free to send that to us. We can forward that along as needed. Thanks again for everyone's time today. And I'm going ahead and stop the recording